Thanks everyone for coming. As Kabir said, I'm a solutions architect at Databricks. I have a degree in applied math with a minor in physics, and I've been using Spark for about the past 5 years. Today I want to talk about a few techniques that I've used and some of my colleagues have used in the past for improving interactive query speed over very massive delta tables. The agenda for the talk here, we're going to do a brief overview of what delta lakes are, the core abstractions that enable the techniques that we're going to be using, cover dynamic range partitioning, which is a database technique that we re-implemented over delta tables. Briefly cover data skipping, how that can affect interactive queries, and how one-dimensional sorting or multi-dimensional clustering can improve that. And briefly cover using streaming queries rather than interactive batch queries. And at the end, we'll talk about future work that could be done as well. What's not in the agenda today, unfortunately, is a silver bullet that will magically make all of your queries very fast. I think we all know that no matter what, you have to constantly maintain your tables and your data, constantly survey your access patterns and how people want to query the data, and improve the performance for those specific use cases. So briefly, what is Delta Lake? I'm sure you've all heard about it or are using it in some way or thinking about using it. Fundamentally, Delta Lake provides ACID transactions over Parquet tables. And this core functionality is accomplished using the delta log, which we'll also briefly dive into. It also scales the metadata by storing all of the metadata next to the actual Parquet data itself, and then using Spark to manage that metadata. So you can easily scale up the size of your metadata, such as the number of partitions, easily into the millions or tens of millions. And then it uses Optimistically concurrent write protocol, so in order to determine whether or not two transactions conflict. And then the nice thing is that it gives you essentially infinite scalability on the reader side as well. So you can have hundreds or thousands of readers all consuming the same delta table. And it's not the metadata that's going to be a bottleneck. It's merely whether or not your storage can tolerate that many readers. And of course, it was designed for Apache Spark directly. So briefly, the transaction log is stored right next to the data. Every time you write files in a batch to a delta table, you get a JSON file containing the list of files. And every 10 JSON files, we then checkpoint this state of the delta table into a Parquet file. And so at the end of the day, when you go to actually read your table, it's querying the metadata as Parquet data and reading it in using Spark. So the metadata reading scales up with the size of your Spark cluster. And that means that something like the Hive metastore and a database is no longer your bottleneck and is not a separate tool that you need to be managing where you need to constantly resize your database for your Hive metastore. As I said, every transaction leaves a new JSON file here, and then they are ordered in a specific way that makes listing very fast on object storage. So that's maybe the other thing I didn't mention is that Delta Lake was designed for object storage first. By solving this harder problem, you actually get HDFS compatibility out of the box as well. Whenever two transactions are occurring at the same time, Delta uses what's called optimistic concurrency to determine whether or not these two transactions can go through together or if one needs to be canceled. There are a few different types of concurrency styles. Optimistic concurrency assumes that most transactions will not conflict and that it's always okay to retry your operation. So if it does detect that two operations are going to conflict, like you're trying to modify files in the same partition and you might be having two writers modifying the same file, the first one to make a commit will succeed. And the second one, when it goes to make a commit, it will see that someone has already modified this file and will be failed. You can simply retry that operation. Optimistic concurrency is preferable in a distributed setting because the other end of the spectrum is pessimistic concurrency, and that's where you assume every transaction will conflict, and so you never allow two transactions to occur at the same time. There's many use cases in databases where you do need that kind of concurrency, but here in a distributed writer setting, optimistic concurrency works well for Delta Lake. As we said, the metadata itself gets checkpointed into Parquet, and then these Parquet files as well get compacted down the line. And so you can very easily scale up the metadata into the hundreds of millions or billions of files in some people's use cases. And then the thing that we're going to talk about today for dynamic range partitioning is the replace where functionality. So you can transactionally overwrite a partition in a Delta table. And this is going to end up being very useful for when we want to resize our range partitions. This is also preferable relative to Parquet tables, where you might be having to write the partition to a separate location, then alter the metastore and add a new partition, remove your old partition. This gives you true transactional consistency on your Delta table. So range partitioning is a database technique, and we'll cover what exactly it is, but what is the motivation for wanting to do range partitioning? As we all know, most of our data is either coming in continuously or we might be getting large batches all at once. Real world data is always skewed, and I put a little asterisk there because sometimes you do end up with uniform data, but I would say that's the exception, not the rule. And you don't know the distribution of your data ahead of time. In some cases as well, you can have some expectations about what the data looks like coming in, but most likely until you have the complete data set, you won't know the true distribution. And partition pruning is very useful. Partitioning is a very useful technique for limiting the amount of data that you need to scan, unless it's not useful. And we'll see an example very quickly. So I have a background in e-commerce, and Black Friday, Cyber Monday are popular shopping holidays online. This is a graphic from Criteo from 2018. You can see that sales have quintupled on Black Friday, and traffic across the board is up 2 to 3x. However, if you've ever worked in with any systems that actually track user events, the number of user events that you will get on a day like this on a massive sale, it can be 10x, it can be 100x. For smaller retailers, they can get 10,000x the normal traffic if they have a very popular sale going on. And so what this ends up meaning is that you might be normally partitioning your data by date, and in a normal day, you don't really have enough data. The date partition works very well. But on Black Friday or on Cyber Monday, you'll have so much data that you actually will want some kind of sub-partitioning on that day, because otherwise you'll be scanning hundreds of terabytes just for that one day. And this is what I mean by partitions are useful until they're not. So range partitioning is a database technique, and the way most databases will implement it, this one's pulled from Oracle, is they'll actually allow you to logically group multiple tables into a single table reference. And so here, this has been range partitioned on a particular column, and you specify which table contains which ranges of the values. This is very nice because it naturally load balances your queries, and you can distribute the data in a more uniform way and get consistent query performance over this table, even though the data may be skewed. And here we're just showing sort of standard range partitions where there's 1,000 values in each one. But what can be more useful is actually looking at the distribution of the data and dynamically determining what the ranges are so that you actually have a consistent size to all of your range partitions. And horizontal partitioning sort of looks like this as well. These are other techniques for it. And maybe if any of you have ever used Cassandra sharding is very similar as well. So what we can get out of dynamic range partitioning, and this is taken from a project where we implemented it, every partition, these are the number of megabytes in each partition. We're able to get it fairly consistently right around 20 gigabytes. That was initially targeted based on the size of the cluster that we wanted to be interacting with the data with. With some, I'll go through the actual steps to produce these, but this ends up being the very nice distribution of data. And you can see sort of where there's specific boundaries, and these boundaries are basically the end of a day, and so the final partition is a little smaller. But across the board, it's fairly consistently between 18 and 22 gigabytes. So number one, you want to wait until the partition is complete, or as complete as you can get it, and then assess the size of that partition. So assess the size of a particular date of data maybe, and look at what the actual distribution is, and then determine how you want, what is going to be a good logical grouping for the actual ranges. So in something like web traffic, you might want to do hourly ranges. Right between sort of 10 p.m. and 6 a.m., you're not going to get that much traffic. But then, midday, maybe you want a range just from 11 to 12. And we can use delta's replace where to dynamically update these subpartitions after resizing and determining what distribution we want to use. So what I've done in the past, what I like to do is use heuristics for determining how big of the partitions you want to use, and essentially deciding how many rows should go in a single partition. You can use a fairly large number, something like 1 million or 10 million rows, to get an idea of how much actual physical disk space that corresponds to in your Parquet files, and then use that to determine what size of partitions you want. So maybe you want every range partition to have something like 20 million rows, because that's a good size of data for the partitioning. In the actual data frame, you can import this data frame stat functions module, and there's an approximate quantile method there. The approximate quantile method uses a pretty cool math algorithm that I definitely won't go into today, called the Greenwald-Kana algorithm, and it's at the moment the highest performance approximation for quantiles. The approximate quantile method also lets you specify the accuracy that you want to go to, and it's quite accurate down to in the approximation, actually. And then you give it as well the column that you want to find out the approximate quantiles for, and the number of quantiles that you want out of the data. This will then give you back your range boundaries. You can take those range boundaries and write a UDF that takes in your input column and outputs the ranges themselves. And I'll show you an example of that in a second. And then you can go in and just overwrite the partition with its new subpartitioning structure using the replace where syntax. So here's an example of some queries hitting this table. And so this is about a 2 petabyte table. And because the queries are very specific and narrowed down to essentially 1 or 2, maybe 3 partitions at any given time, we were able to get the query performance down below 12 seconds without any caching. And then if you want to cache some of the data on the local SSDs of the executors, we were able to get those queries down to 3 seconds. And perhaps the coolest part is actually the size of the cluster and actually how cheap it was to query this table, but also that this was able to easily scale up more than 20x over the course of a few years. So these 3-second queries are actually, this data is, you're hitting a 2 petabyte table with just 72 cores and a few terabytes of SSDs, but you're able to get these 3-second queries out of it. The overall actual cost for running this cluster was only $100 per 18-hour period, so something like $900 per week, basically, for the actual customer. And then, as we said, the The data itself, this was initially just sort of a 50 terabyte data set, but we had a need to eventually scale this up to many petabytes, and this technique was able to easily scale up essentially infinitely because you're only adding partitions that are the same size. And so as long as your queries are limited to those partitions, you'll always get the same performance out of it. So in order to actually resize and replace the partitions, I've made a small example here. And so you can do simple ranges just as strings with a delimiter between them. And then what I like to do is write a little query library that will translate your query into the proper filter for the ranges. So if I have these partitions to start with, and then maybe I need to add more data into them, what I can do is I can add data to those partitions, but then reload them and resize everything and change the ranges. So here I have ranges going from 1 to 5, 6 to 7. I'm going to change these ranges in the next couple slides. The syntax is very simple. So you simply specify what the partition is that you want to be overwriting, and you give it the same partitioning structure from a data frame that has the updated hour ranges in the overwrite mode. And then what you get is now new hourly ranges. So here I've switched the top range from 1 to 4. We have a bunch of traffic from 5 a.m. to 6 a.m. So at a further granularity below range partitioning, you can actually get data skipping as well. Data skipping right now is on the roadmap for open source Delta. And what data skipping does is it collects min-max values for every column in your Parquet files, and is able to use that metadata to skip files. So it's able to look at whether or not your particular filter whether or not these files contain any values for that particular filter. It's able to do that. Then within your partition itself, you're able to even further narrow down which files you're going to be loading. And in Databricks, we have this nice tool for Z-order indexing built in, and it's a built-in feature into the Databricks runtime. But this technique is actually fairly well documented, and it's actually not too bad to implement something like this yourself. The other thing is that data skipping is effective even if you're not using a multidimensional clustering technique. If you're simply sorting on a single column, and your queries are mostly going to be filtering on that sorted column, you'll get very effective data skipping. Here what Z-order does is it maps the data into a binary space and then sorts it there. And what you end up getting is this natural clustering of data into what's called Z-cubes. So then rather than doing a linear row traversal, you're able to sort of filter data in this slicing way. However, Z-order has a limit to how effective it can be because it's just mapping into a binary space. And so effectiveness does fall off after 3 to 5 columns. Or if your data is really not co-grouped together in any way, not correlated, then Z-order will not end up being that effective. Down the road, it would be really interesting to implement the Hilbert curve, which is a different space mapping curve. The Hilbert curve has higher dimensional effectiveness, essentially. So it's not quite as effective on small numbers of columns, but it scales up much better into 5 or even 10 or 15 columns and is able to co-locate the data. So when you go to tune your actual file size, there's a few considerations to take into account. Smaller files and bigger files both have pros and cons is the thing, and you essentially want to look at your use case and tune for that, right? When you're doing data skipping, if you have smaller files, you can obviously skip more of them potentially. But on the inverse, if you're not able to skip more of them, you will end up making more file open calls, and that can add overhead. The other thing to take into consideration is how your storage medium is charging you. S3 itself charges per put request, and so if you are writing larger files, that will reduce your cost of writing the data to S3. And then if you're doing updates as well and using merge, the updates can either be more granular with small files, or they can actually have to scan and touch more files. Bigger files have other benefits, like if you are writing a massive amount of data and you try to write too many files to object storage, you may end up either being throttled or being told your job will fail because you've DDoSed the object storage. So bigger files will help on that side. And then if you're being charged per load, S3 as well charges for GET requests, and so you'll have cheaper access costs if you're loading bigger files and using the data. However, the other trade-offs apply. So if you are trying to update data, you may end up updating a larger file where you could have updated a much smaller file. And then for tables that are designed to be for interactive query use, right, you have this sort of trade-off of recency versus performance. So it's very easy to tune a static data set that is never changing. But if you want to get to the latest data, generally that's not going to be as well optimized. And what can help with that is using streaming to run your queries instead of running them in a batch interactive mode. What streaming will do is, structured streaming has support for checkpointing and incremental processing. And so you can actually set your query, and then whenever you are getting new data, you can simply restart your stream and then get access to the latest results, update results. And then again, with Delta Lake as a streaming sink, you can be streaming your changes into Delta using the merge framework, and then essentially use Delta as your state storage. So then you're not required to store a lot of state in memory or on disk in your actual stream. You can offload that state into the Delta table. And the last thing is that you really want to sit with your users a lot. This is something that's really important, is you want to survey and be constantly communicating with the people who are consuming your tables, and seeing how you can support their query profiles. With range partitioning, right, you're sort of limited to a single level of sub-partitioning, a single column or two columns. But it may be possible to map other queries that users are running to the range partitioning itself. And so even though you're not limiting yourself to a single partition, you may be able to map some of their queries to a few partitions across the data set and still significantly limit how much data you're scanning. And generally, the way I prefer to do this is to develop libraries that abstract away the low-level querying for the users and give them direct access to the way that they want to query the table, and abstract away the performance tuning that's being done underneath. And worst comes to worst, you also may end up just having to duplicate some of your data in order to support query profiles that just won't work with your existing structure. And so the future work that I wanted to talk about quickly is in Spark 3, there will be support at some point for what's called computed partitions. And those are where you actually have sort of a derived value from another thing. So if you have a date partition or you have an hourly partition, you can actually compute the date partition from the hourly partition without having to have the date partition physically there. This can be really nice because then you can have that lower level granularity of partitioning and still get higher level logical partitions without having to physically manifest them. What I think would be cool is if range partitioning also would be either built into Spark or supported as a separate library. And then also right now, most of the code I've written has been fairly manual to run the actual range sizing. It'd be nice if that could be automatically determined as well. And then you can simply, as you are updating your table, you can run the dynamic range sizing and determine the new ranges for your partitions. And that's it. I actually have a bunch of time for questions. Thank you.
Thank you very much for your talk, Chris. So we have ample time for your questions. So there is one mic there, and I will be also walking around with the microphone.
Yeah, we talk about like concurrent readers, concurrent writers, right? So there is some use cases like structure streaming. So I'm getting data from the sensors, okay?
Sorry, could get a little closer to the mic? I'm having trouble here.
Okay. So my question is about like, we talk about like concurrent readers, concurrent writers, right? So my use case, like I'm getting data from sensors, IoT sensors data. Then I create a delta table, right? So keep on storing the delta table. On the top of that, can we create a multiple table by using different partition? This is one question. Second question is like if when you use the structure streaming, right? Normally the data will go and write as a small file, right? So by using the data latest feature, I can use auto-optimize, auto-compact by the users. By using this one, that file will be, instead of small file, that file will be huge. So in this case, how do we the performance-wise? So that's the two questions I have.
I'm really sorry, I didn't catch the last
Okay.
part. I'm having, there's a bit of echo.
Okay, so the first question is, I have the delta table, okay?
Yeah.
I create a delta table. The source of the delta tables, multiple streams, which comes from IoT sensor, right? So now, the top of that delta table, can we create multiple delta table, which for the interactive queries for the different use cases? Is it possible?
So you want to create like multiple logical views over the delta table?
Yeah.
Yeah, you can definitely create views over the tables and support a few different query profiles in that way. But they sort of do have to be logically similar in order to work well in this framework. So otherwise. What would be really cool is if you could have a single delta table, but maybe Z-order on separate ways, index it in multiple different ways, right? Sort of get closer to secondary indexes from databases. But that's something that sort of hasn't been taken up yet. I think long-term though, right, the core of Delta Lake is really bringing the principles of databases to big data over object storage. And I think long-term, these sorts of features are going to start being developed in the community. Okay.
So second question is about, since we use a structure streaming, right? So when you write into the delta table, the result will be small file, right? So I can use auto-optimize the new features, which is provided by the Databricks. So instead of small file, I can write a big file based on that latest, the data, the outbounded table, right? So my question is over here, so how do we, performance-wise, if I take how it will be different since?
Yeah. So the way Optimize Writes and Auto-Optimize works at the moment is essentially designed to not DDoS object storage. So it takes your stream that's writing tons of small files and turns them into slightly larger files. Right now, Auto-Optimize targets 128 megabyte files. And then Optimize itself will compact the files into larger files, into 1 gigabyte. But as I mentioned, with the actual data skipping, it's usually more effective to have smaller files in order to get more effectiveness out of the data skipping.
Thank you.
Okay, it's this. I don't know, but I think that my question is similar. I made some tests receiving data from, I don't know, Event Hub, real time. And I try to use optimize command to shrink all small files, keep Kbytes to large files. And it doesn't work to me, and my query process will take too long, and I had some problems with performance. I don't know, I'm trying to make real-time fact table, something like that. So what can I do to do this, to solve this problem?
So I'm not sure I got what part was failing for you?
Okay, I try to use optimize command in my stream table, okay? But the stream table don't do the command. They don't shrink the table, and I didn't find nothing about it, and I just try to know if, I don't know, doesn't work at some cases, or if I need to do another thing, I don't know.
No, you should be able to set it at the table level, but that's probably something that it might be good to look at that either sort of at the advisory bar or through your support person, I think.
Okay,
yeah,
no problem.
that sounds like it's not supposed to be happening that way.
Just one more thing, that's difference between external and internal tables to this, because I try to do with using external table, moving the files outside of the Databricks. I don't know if has
Right. And so you can read Delta tables using the open source library from any Spark cluster.
Okay.
Right now there's support to export sort of a static view of the table to Presto or Hive. But long-term, we are working with the Hive and Presto communities to develop first-party readers for Delta, so those query engines can read the Delta log themselves.
Okay, thank you so much.
The Z-order type, is this just for numbers working? Because it is min-maxing the stuff, and it is not for strings, though?
Right, exactly. So the Z-ordering just helps co-locate data in a couple columns, and then the min-maxing is what actually accomplishes the data skipping. Yeah, so collecting those statistics, you have two options. You can either collect those statistics on write at the end of every commit. That adds a little bit of latency to every commit that you make to the table. Or you can defer the collection of statistics till after you've finished writing and maybe run that asynchronously and run a statistics collection job. Yeah, but the main reason is actually that with the Hive Metastore, right, you can also collect statistics. You can run analyze table and use that for the CBO. But it's very easy for those statistics to become out of date. And actually, as soon as those statistics are out of date, they can very easily negatively impact CBO. And so collecting the statistics after every batch write helps you make sure that those statistics are actually up to date for planning.
Chris, thank you very much for your talk. I have a question about, in, let's say, non-Delta tables, I have the option when storing the data to say bucket by, and to ensure that I write the table in the same way that it's going to be partitioned in the cluster and optimized for, let's say, the users for joins and that kind of stuff. In Delta, do I have a same option, or does, let's say, optimize help, or what's the solution in that case?
Sorry, what were the last couple words?
So, well, actually, what's the sort of equivalent in Delta tables to, let's say, the non-Delta bucket by, to make sure that you kind of have your data prepared already for how you want to partition it in the cluster?
I'm sorry, I still can't catch it. I'm getting this weird echo from the speakers.
Okay. So I'll repeat quickly. So yeah, when I store my data in the non-Delta table, I can say bucket by. If I say bucket by, then it's getting stored in files that are already in the same, let's say, stored already across.
Right. Yeah, so Delta has the exact same folder structure and layout as a normal Parquet table. The only difference is that transaction log is also there. So you have your top level directory for all the Parquet files, and then you also have a folder for the Delta log. And that's really the only difference. And so actually, also, if you use the if you vacuum the table and clean up all of the old Parquet files, you're actually left with just a regular Parquet table as well.
Hi, that's a really cool feature you described in range partitioning. So I was just wondering, what's the overhead of running replace where compared to, let's say, optimize?
Yeah, that's a great question. So in this particular case, the first time I implemented it, they had a unique use case, I think, where they needed to rewrite the entire table every time. So they would get like a new batch of data, increasing, you know, the data size from 50 terabytes to 100 terabytes. And they would need to rewrite the entire thing and redetermine all of the range partitions. I think if you have data that's coming in more continuously, it's a lot easier. Like the date example makes a lot more sense, where you simply at the end of every day or maybe a week afterwards, you can go back and update the range partitions very easily. There's a bunch, I didn't put any of them in there, but there's a bunch of, like, depending on the object storage you're using, there's a bunch of configs you can use that will help you accomplish these writes. Because there is a fair bit of like trickery to how to get the multi-part uploads and all of these things working correctly. So if that's interesting, I can definitely like talk to you afterwards.
Hey, great talk.
Thanks.
Is there a solution for Delta? Is there a solution for CDC on Delta? Because I need to maintain my legacy database in RDBMS.
Yeah. So Databricks implemented a MySQL CDC connector where you can hook into the change logs of a MySQL table. But it's sort of a lot of work to actually implement it for every database. I think this is probably something that makes more sense to do in the community instead. And then community users can implement the CDC log for whichever particular database they are using. But then the other thing is that right now you can use batch and streaming to CDC between Delta tables, use the merge framework to merge your changes into Delta. But at the moment, it's not, how do I want to say this? It's not easy. Or it's not, you know, like out of the box, it just works. Like you can't just say this Delta table is the changes from this other Delta table. I think long term, especially the Delta pipeline stuff that Michael wants to work on, that's going to help a lot, where it sort of abstracts away the low level stuff of how do you connect these two data sources together logically. Instead, just lets you say, I want this table to capture all the changes from this other table. And then downstream, you can have a consistent view of that.
Just tell Michael to focus on the other way around, to CDC a Delta table, because the new system is a Delta table, and we need to maintain the old one. So capture the changes on the Delta table and push them down to the old legacy system.
Oh, I see.
Because old users still use the old system.
Oh, yeah, okay. That's actually a lot easier to do. So that's actually pretty easy to do with streaming right now. You can pretty easily just, as you're streaming from the table, you'll get the correct order of those changes. Other ways I've seen people do it is, you know, like they are piping changes into a Kafka server, and then either like reading those from structured streaming and writing again to Kafka, or updating a database. That's something I also haven't covered, but with Spark 3 is going to have data source v2. And data source, the second version of data source is going to expand a lot what data sources are capable of in Spark. So one of the limitations right now with the JDBC writer is it can only append to a table or overwrite a table. Data source v2 is going to allow a JDBC data source to have an update mode, where you can actually write to a table and update it in the way you expect it to work.
Okay, thank you very much for your questions. That's all. We are out of time. And thanks again, Chris, for your talk.
Thank you.